Welcome to General Chemistry Mini Lecture Series, Lecture 42, Lattice Energy and Born-Haber Cycle. Unlike covalent bonds, ionic bonds are non-directional, and there are no direct anion-cation pairs. That is also why there are no ionic molecules. So the chemical formula for ionic compounds is just the empirical formula. The ionic formula simply gives the ratio of ions based on charge balance. A collection of ions in ionic compounds arranged in a pattern that is called a crystal lattice. Every cation, the red dots, is surrounded by anions, the green ones, and every anion is surrounded by cations. This pattern maximizes the attractions between the positive and negative ions. Lattice energy is the energy released when solid crystals form from separate ions in the gas state. Lattice energy is always exothermic. Gaseous cation reacts with gaseous anion, forms ionic compounds. Lattice energy is released during that process. Lattice energy is always exothermic with a negative value. The lattice energy released comes from the formation of crystal lattice. And in this specific structure, every cation is surrounded by anions and vice versa, as I just pointed out in the previous slide. The crystal lattice maximizes the attraction between cations and anions, and this leads to the most stable arrangement. If we use sodium chloride as an example, gaseous sodium ion reacting with gaseous chloride, forming solid sodium chloride. And during this reaction, lattice energy is released. Therefore, this crystal formation process is exothermic. Heat is released. Now let's go over how to predict lattice energy. Lattice energy is directly proportional to the charge of the ions and inversely proportional to the distance that separates the ions. Lattice energy decreases with increasing principal quantum number, n, as well as the period in periodic table. That is because the ionic radius increases down a groove, and the distance between the ions is inversely proportional to lattice energy. That leads to an increasing lattice energy with decreasing n values. In short, the lower the n value, the higher the lattice energy. It is obvious that lattice energy increases with increasing charges because the product of the charges of the ions is directly proportional to lattice energy. Now let's look at the trends in lattice energy for alkaline metal halides, which means the compounds formed between group 1A cations and group 7A anions. First, let's take a look at the series of compounds formed with fluoride. We already have lithium fluoride, and here should be sodium fluoride. Let me write it down. This one is a sodium fluoride. Now potassium fluoride and rubidium fluoride. Because all of the 4 compounds contain the same anion, which is fluoride, the R value is determined only by the size of the cations. As we already learned previously, cations in the same group increases from top to bottom. Therefore, the R values for those 4 compounds also increases from top to bottom. But as we can see right here, the lattice energy is inversely proportional to R value. It means the lower the R value, the higher the lattice energy. Therefore, lithium fluoride has the highest lattice energy, while rubidium fluoride has the lowest energy among this series of ionic compounds. Now let's take a look at another series of ionic compounds. They all contain sodium cation. This one is a sodium fluoride, and this one should be sodium chloride, sodium bromide, and sodium iodide. Let me write them down. This one is sodium fluoride, sodium chloride, sodium bromide, sodium iodide. All of those 4 compounds contain the same cation, which is the sodium cation. Therefore, the distance between the ions, the R value, is determined only by the size of the ions. If you look at the radius of those ions, it increases from fluoride to iodide. Now we know the R value for compounds in this green series increases from sodium fluoride to sodium iodide. Based on this lattice energy equation, the larger the R value, the smaller the lattice energy. Therefore, sodium iodide should have the lowest lattice energy, while sodium fluoride should have the highest lattice energy. This is how you predict the trends in lattice energy for ionic compounds. Now let's work on the first example in lecture 42. We need to determine which of those 5 compounds has the largest lattice energy. Recall the lattice energy equation. Let's take a closer look at compounds 1, 2, and 5. They all contain sodium cation, which is positive 1, which carries a charge of positive 1. And all of their anions, they carry a negative 1 charge. So therefore, the product of their charge values are smaller than in compounds 3 and 4, because here the cations carry positive 2 charges. Now we focus on compounds 3 and 4. Both have cations with positive 2 charge, which means Q1 times Q2 should be the same for compounds 3 and 4. Therefore, the lattice energies of the 2 compounds depend only on the R values. The distance between the ions, or the R values, can be estimated using the ionic size. And here is the trend for ionic radius. From this equation, we know the smaller the R value, the larger the lattice energy. Both compounds 3 and 4, magnesium chloride and strontium chloride, contain the same anion, so their R values depend only on the cation size. Now let's find out which cation is larger. In order to do that, let's locate the 2 elements. Magnesium is here, strontium is here, and the trend of increasing ionic radius is from top to bottom. it means magnesium ion is smaller than strontium ion. That leads to the R value for magnesium chloride smaller than the R value for strontium chloride. Therefore, magnesium chloride has the largest lattice energy. The second largest has to be strontium chloride. Now let's work on example 2. We need to arrange the same 5 compounds as we just worked on in example number 1 in order of increasing lattice energy. Again, let me bring up the equation for calculating the lattice energy. In the previous slide, we already know magnesium chloride has the largest lattice energy, followed by strontium chloride. Then we only need to work on compounds 1, 2, and 5. They all have the same Q1 times Q2 values because they all contain plus minus 1 ions. Then we should be able to just use their R values to determine their lattice energies. Because all of these 3 compounds contain the same cation, which is a sodium ion, then the R values only depend on the anion size. Now let's find out the elements of the 3 anions. Fluoride is formed from fluorine, chloride is formed from chlorine, iodide is formed from iodine. So the size for the ions should increase from top to bottom. That means sodium iodide has the largest R value, sodium chloride has the second largest R value, and sodium fluoride has the smallest R value among compounds 1, 2, and 5. 1, 2, and 5. Now we are ready to answer the trend in lattice energy. Because lattice energy is inversely proportional to R value, the opposite trend for the R value should be the trend for lattice energy. Therefore, sodium fluoride has the lowest R value. That should result in the largest lattice energy. That's why sodium fluoride has the largest energy, followed by sodium chloride, and sodium iodide has the lowest lattice energy. Now we can put the 2 groups together. The first group, compound 3 and 4, we already solved that in the previous example, example 42-1, and we just worked on the remaining 3 compounds, compounds 1, 2, and 5, in the last couple of minutes. So we are ready to give the trend of lattice energy for all 5 compounds. That should be sodium iodide has the lowest lattice energy, while magnesium chloride has the largest lattice energy. This is how you predict the trend of lattice energy in a group of ionic compounds. Born-Haber cycle is a hypothetical series of steps that represents the formation of an ionic compound from its constituent elements. We can use Born-Haber cycle to calculate lattice energy. When metal reacting with nonmetal to form an ionic compound, the first step of the reaction involves the evaporation of solid metal to gaseous atoms. That step of reaction is called sublimation. Second step is the dissociation of nonmetal to gaseous nonmetal atoms. In this case, from diatomic molecule like chlorine, bromine, iodine, and so on and so forth, to gases, chlorine, bromine, or iodine atoms. Therefore, step 2 is a dissociation of nonmetal. Step 3, it is the ionization of the gaseous metal to gaseous cations. So this red part, we call that ionization of metal. Step number 4 involves electron affinity. Nonmetal atoms receive electrons, become anions. So therefore, step number 4 is the electron affinity of nonmetal. Step number 5, that's the formation of solid crystal from gases, cation, and anion. And during this step, lattice energy is involved. Therefore, step number 5 is the lattice formation of solid crystal. Through these 5 steps, solid metal reacting with a gaseous nonmetal, forming solid crystal, ionic compound. So therefore, the sum of those individual steps, I call that overall. That is actually the formation reaction of the solid crystal. This is called Born-Haber cycle. Here is another way of showing the Born-Haber cycle for the formation of sodium chloride from solid sodium and gaseous chlorine diatomic molecule. And the data H for each individual steps are given. Then using those data H values, we should be able to calculate the heat of formation for sodium chloride. According to He's law, the data H for this overall step can be calculated by adding other individual steps, step 1 and 2, 3 and 4, and 5. Where do you get those data H values? They are given right here. Step number 1, sublimation of solid, and the data H for the first step is positive 108 kilojoules. Then step number 2 is the dissociation of chlorine diatomic molecule. That data H value is 122, or 1/2 of 244. Step number 3, ionization of sodium, positive 496. Step number 4, electron affinity for chlorine, negative. That's exothermic now. Negative 349. Number 5, lattice energy, and that's a negative 788 kilojoules. If you add those together, cancel the spectators, you would just have sodium in solid state reacting with 1/2 of Cl2 in gaseous state. Then on the right hand side, you should just have sodium chloride crystal. Then you have to do the same. You add all of those individual data H values. If you do that, you will end up with negative 411 kilojoules. And that is the heat of formation for sodium chloride. Let's work on another example. Calculate the lattice energy for sodium chloride using the enthalpy values shown on the left. Before we work on it, let me modify the information given on the left. This value, instead of it's given, it becomes unknown in this example. So we add this piece of information to example 4. So now we should be ready to solve the problem. Because the data H for this overall step is the sum of the data H in steps 1 through 5, 1 through 5. And now we want to find out the delta H in step number 5, so which means we don't know the value here for step 5, which is the lattice energy. Then what do? We use this value, that's a delta H for the overall reaction, or the delta H of formation, subtracted by the sum of the first 4 steps. So this is the delta H formation, or the delta H value for the overall reaction, negative 411, subtracted by the sum of the delta H value in step number 1, step number 2, step number 3, and step number 4. The answer should be the lattice energy for sodium chloride, and that's negative 788 kilojoules. Therefore, you can also use Born-Haber cycle to calculate lattice energy, not just the delta H of formation reaction. That's it for lecture 42. If this video is helpful, please subscribe to this channel and recommend the videos in this channel to other students who are also studying chemistry. I will see you in lecture 43 for more charge and resonance structures.